So the other option we have is in terms of fusion and fission. So before we talk about it, let's this energy that comes out of these reactions is expressed in terms of a million electron volts, and that's a pretty small of energy. It's given by this number in kilowatt hours, but there are so many reactions that are taking place that it amounts to a large amount of energy. So starting with nuclear fusion, that's the process that goes on constantly on our sun, where let's say two atoms like deuterium atoms, they fuse together and they create this tritium atom, they release a proton and then some small amount of energy here. Okay, so this is a process that has been replicated in research labs, but there's no practical power plant built based on nuclear fusion today. So if this were to happen, then we will have plenty of fuel, because this is basically water here. Okay, so that'll be very nice, but there are some great technical challenges, because the plasma that is created is at millions of degrees, and to contain it and not letting it hit the reactor walls is a great challenge. So in spite of these challenges, research goes on in nuclear fusion. The other type, which is a more common type of nuclear reaction that is used in nuclear power plants, is a so-called nuclear fission. Here what happens is, if you take a uranium atom here, you bombard it with a neutron, then it splits up into smaller, lighter weight atoms here, and 2 neutrons are released, and in addition, this amount of energy is released as well. So if, let's say, one of these neutrons out of these 2 strikes another uranium atom, and so on and so on, then we have a chain reaction. And if it's a controlled chain reaction, then we have a nuclear reactor. So this is a process which takes place in nuclear reactors. And there are 2 nuclear reactors, 2 types, I should say. There are more, actually, but there are 2 common ones. One is called a boiling water reactor. Okay, and here what happens is that you have a reactor vessel, and the coolant itself goes to the turbine and the condenser and the pump. So there's only one cycle, as you can see here. Okay, so these were built in the past, and you can look up this website, and this is where I got this picture. And here, since the same coolant that we have, which is also sometimes called moderator, in the reactor vessel goes to the turbine and condenser, there's some chance of radioactivity getting into turbine and condensers and so forth, although it's pretty remote, but quite often the power plants that are being built more and more are using so-called pressurized water reactor, PWR. Okay, so here there are 2 distinct cycles. One is this coolant and moderator through this nuclear reactor over here, and then the heat that is carried by this coolant, shown in red, is then transferred to this another cycle, and here steam is generated, and just like we had seen this Rankine cycle, we have this steam under high pressure going into the turbine, and then the condenser cooling it to water, and then the pump making it high pressure. So you can see that there are 2 separate links, or loops, I should say, 2 separate loops. And again, this picture comes from this website here, which you can look up. So you can see here that this is somewhat safer, but both are very safe. There has been no problem as such. Now, turning to renewable resources, One of them is wind resource. And at least in the United States, it's very plentiful. Anything you see in pink is excellent. It's very good, actually. And of course, anything in purple here is excellent. But the problem is that wherever it's very windy, people are not living. Okay, and that is also true. For example, in North and South Dakota, have tremendous wind resources, but very few people are living there. Okay, the population centers are elsewhere, so that energy which is derived from wind has to be transported long distance or transmitted long distance. So that's a problem of wind, and similarly in Minnesota, in southwestern part over here, very good wind conditions here. So if you look at here, better would be to say a proportionality sign, unless we have the right units here. And let's not talk about that. And this graph should be really cut off here. This was created by a computer over here. So you can see that the power in the wind is proportional to wind velocity cube. So it's a very nonlinear function of wind velocity. If the wind speed were to double, then the power would be 8 times. Okay, and then of course the area swept by the blades and the density of air, and then not. So this is in the bracket. You can say is the energy that is in power and wind, but not all of that can be derived. Okay, so that's in the kinetic energy of wind, but not all of it can be harnessed. So there's this this coefficient here, which is called coefficient of performance. Okay, and it can be shown to be theoretically about 59.3% or something, but in reality it's close to 0.48, 0.5, something like that, 48 to 50%, and that's its maximum value. And it is a function of so-called blade tip speed ratio. So this lambda is the speed of the blade tip, and that is, as you can see, would be equal to the speed at which the blades are rotating times their radius, right? So if you multiply the two, that gives us the speed at which the wind, at which the tip of these blades are traveling. And if you divide that by the wind velocity, that gives us this lambda. And you can see that if you can adjust this lambda, then we can obtain this maximum value of this coefficient of performance. So the curves that are plotted for different values of pitch angle of the blade. So let's say that you want to capture all the wind, then the pitch angle is 0 or close to 0. And so if you just concentrate on this curve, you can see that we can get this to be as high as 0.48 or something like that. But that's provided we can operate at this lambda. Of course, we cannot control the speed of wind velocity, but if we can control the speed at which the blades are rotating, then we can control this lambda to give us the maximum CP. So what are the different types of wind turbine arrangements? First of all, I have not shown the gearbox over here. So a lot of these turbines have a gearbox because these blades are turning at pretty low RPM, 10 to 20 RPM, let's say, and this induction generator may be turning at, let's say, close to 1800 RPM. So there's 100 to 1 gear ratio here. But this gearbox is perhaps the weakest link in this chain. So a lot of, actually most wind turbine companies are trying to get rid of this gearbox over here. In that case, the blades will still be turning at very low RPM, but this induction generator will also have to be designed at this RPM over here. So the size of this induction generator becomes very large. So there are trade-offs here. but because of the reliability, to improve the reliability, everybody is trying to get rid of these gearboxes if possible. So in the previous slide, we saw that that induction generator was directly coupled to the grid without any power electronics. So that the whole arrangement would run, maybe I could go back up here. In this arrangement, this turbine here has to rotate very close to the synchronous speed dictated by this utility. For example, this is a 60 hertz utility into which we are feeding the power, and if you're using a 4-pole induction generator with gear box over here, then the synchronous speed is 1800 RPM. So knowing this induction machine theory, whether it's a induction motor or an induction generator, it will run very close to the synchronous speed, not at the synchronous speed, but close to synchronous speed. So the point I'm trying to make here is that if we have this arrangement, then we have no option, but the whole system would run at a fairly, in a very narrow range of speeds, right? So, and you can see here that this has to be run as a generator, and one of the drawbacks of this system is that this would always consume reactive power from the grid here. So it'll, as far as the grid is concerned, this arrangement would look like an inductor. Just like an inductor draws reactive power, this would also draw reactive power, because that's what induction machines do. Whether they are, this is a squirrel cage induction machine, and whether it's running as a motor or a generator, it will draw reactive power. So that's a drawback here, because it should be, as we will see later on, we should be able to supply reactive power. So in order to do that, a fairly popular scheme is so-called doubly fed induction generator. So in this arrangement, again, I am not showing the gearbox. The stator of this induction generator is directly connected to the grid. So here's the grid. Okay. So once again, there is no power electronics between the induction generator and the generator stator, I should say, and the grid. And most of the power flows directly from the stator to the grid. So let's say about 75% or more power, maybe even greater than that, flows directly. And in this case, instead of having a squirrel cage induction machine, we have a wound rotor induction machine, where the terminals of the windings in the rotor are brought out to a slip ring. And on these slip rings sit brushes, and therefore we can inject an appropriate frequency current into the rotor, some low frequency. Okay, so that's what is done in this doubly fed induction generator, and about 15 or 20% of the power can flow from the rotor circuit here. So this type of arrangement can operate both at subsynchronous, that is below the synchronous speed, as well as above the synchronous speed, whereas the previous arrangement must operate above the synchronous speed. Otherwise, it will become a motor. And we don't want it to become a motor, because then it will turn into a fan. So it must operate at supersynchronous. Whereas here, both of those are possible, above or below the synchronous speed. And in this arrangement, we can either supply or draw reactive power. So this Q here could be supplied or could be drawn here. Maybe I should show it from this grid side here. Q could be supplied to this arrangement, or this arrangement could supply Q in this direction over here. So it's a very flexible scheme. We can control the speed over a certain range. It's not a very wide range, but we can control around the synchronous speed, 10 at 15%, either way, and also provide the reactive power to the grid, and and only 15 or 20% of the power is going through this power electronics, where first AC is converted into DC here across this link, and then this DC is inverted back to some low frequency AC, which is injected into the rotor of this circuit here. So this is a fairly popular scheme. But I think the future is right here. Again, have not shown the gearbox, and which may eventually disappear anyway. So this is an AC machine. It could be a squirrel cage induction machine, or it could be a permanent magnet AC machine here. And here, all the power is flowing through power electronics here. So the frequency here of the voltages and currents in amplitude and in frequency, they are variable. It depends upon the speed of wind and at which speed the blades are turning. So the frequency and the amplitude of voltages produced here would vary. So the role of power electronics then is to convert that incoming power to a fixed frequency, fixed amplitude voltage of the utility. And therefore, we must need a power electronics. So here, as you can see, all the power is flowing through a power electronics. So the cost of power electronics is high, but at the same time, the speed can vary over a very large range. So that restriction is not there. And once again, this arrangement can supply or draw reactive power from the utility, which ends up controlling the voltage on the grid. So that's a very important feature, and this is the arrangement that is gaining popularity. So let's shift gears and let's talk about photovoltaics, solar cells, and sun's energy is so distributed that once these become economical, they would really be a very good source for renewable energy. So in photovoltaics, these solar cells, they produce DC. The cell current is plotted here as a function of voltage here, and it is plotted for different levels of light. And you can see here that if you concentrate on this light level over here, depending upon the temperature, you have different characteristics here. So you can see that at low temperatures, the output is higher. So ideally, we would like as much light as possible, of course, but also a very low temperature, ambient temperature. And the maximum power occurs at the knee of these characteristics, because we are plotting current versus voltage here, right? And the power is current times voltage. So you can see that it really occurs around the knee of these characteristics over here. Okay, so that's called the maximum power point, and that's where we would like to operate these solar cells to get the maximum power possible here. So here is the circuitry shown here. I'm not going to go into the details of this. Here are the solar cells here. Here is, let's say, a single-phase utility. It could be three-phase, and you may want some isolation. You may need to step up the voltage. So this is done through this power electronics. There are all kinds of different arrangements, and we would like to control this such that we are operating at the maximum power points of these solar cells here. So there is a circuitry which allows this maximum power point tracking. Okay. Then we have fuel cells, and again they produce DC, and the fuel usually is hydrogen. But the question is, where is this hydrogen coming from? Okay, and one of the options may be that when you have excess wind, which is perhaps not needed, could be producing this hydrogen by electrolysis. So that's a possibility. But the main point here is the availability of the fuel. Okay. So all of these things lead to so-called greenhouse effect, these greenhouse gases. And just like in a greenhouse, when you have this solar radiation, ultraviolet, that passes through the atmosphere. And then it heats up the surface of Earth, and this heated surface then radiates infrared. And some of this infrared is trapped by greenhouse gas molecules. Okay, so that is what's leading to this greenhouse effect and climate change, which most scientists believe is happening because of these greenhouse gases. So it's a very serious concern, probably the most serious threat, this is my opinion, facing humanity. And here is a website that one could go to and see some animations. So every utility has a resource mix. Our local utility here, Xcel Energy, has a resource mix which is shown here. It's actually quite a bit nuclear here. We have two nuclear power plants, one pressurized water reactor and one boiling water reactor, but a lot of it comes from coal. So every utility has some kind of a resource portfolio like this here. So, we can talk about cost of electricity, and that really varies from one location to another. But the only thing I'd like to say is that cost of electricity from wind has become quite competitive. Okay, although the cost from photovoltaics is still pretty high, but there's always a possibility of breakthrough in photovoltaics, and hopefully that happens and the cost comes down. But there's another possibility with solar, so-called concentrated solar power, where you have heliostats. That's just a fancy word for mirrors, where you concentrate sun's rays on a tower and produce steam and run a turbine. So that is another possibility, and the cost of doing that is quite a bit lower, at least in right locations, compared to photovoltaics here. So this brings us to the end of this module, where we have seen how this electricity is produced and what our choices are, what the consequences are, and what the cost of electricity is. Thank you.